Hi everyone, thanks for watching my contributed talk, and thank you so much to the organizers for giving people an opportunity to submit contributed talks for a virtual conference. So I'm going to be speaking on a theorem that Leonard Wang and I proved. We're calling it the covariant Stone-von Neumann theorem, and it is inspired by a historical problem. The goal of this historical problem is to classify all pairs of possibly unbounded self-adjoint operators on a Hilbert space which satisfy they both share a common dense domain. So given that A and B could be unbounded, that means that they each have some domain in the Hilbert space on which they're defined, and we need a common subspace of those two domains that is still dense in the Hilbert space. And sometimes that is asking quite a lot. But we need that, or else asking that this pair satisfies the Heisenberg commutation relation doesn't really make any sense, or it's just not a very strong statement unless this is happening on a large part of the Hilbert space. So here's an example of such a pair. Consider Q and P. Q is multiplication by X. This is also known as the position operator on a one-dimensional particle system. And P is the momentum operator. The Hilbert space here is L2 of R. These share, for example, the Schwartz space of rapidly decreasing functions in their domains, and that is a dense subspace of L2 of R. So they satisfy the Heisenberg commutation relation on that. Therefore, they are a Heisenberg pair. We called it the Schrödinger pair because this is such a canonical example. And the question is this everything? Are all pairs A and B unitarily equivalent to a direct sum of copies of potentially the Schrödinger pair? This is not necessarily the case. So how do we go about trying to classify these? Because these pairs of operators in a physical setting are representing quantum measurements that one could make, and you'd like to know what pairs of measurements cannot be simultaneously measured to some high level of accuracy, like position and momentum. So the first thing we could do is, because this subspace K is so important, why don't we just make stronger restrictions on it? Not only does it need to be dense, maybe it needs to consist of maybe analytic vectors for both A and B. I won't define analytic vectors, but that is something that I think the Flato-Simon integrability criterion considers. Or because unbounded operators in general are just hard to work with, we could instead, using Stone's theorem, consider the unitary groups generated by the self-adjoint operators A and B and see if they satisfy the Weil commutation relation. So what is that? Well, if we have a locally compact abelian group, and we are going to zoom out just a little bit because, of course, if you generate the unitary groups for A and B by Stone's theorem, they are indexed by the locally compact abelian group R, but we can do something a little bit more general. So we say that that a pair of unitary representations, one of the group and the other of the Pontryagin dual of the group, they satisfy the commutation relation if essentially swapping their orders or intertwining them results in multiplication by gamma applied to X. An example of a pair of unitary representations that do this, and by the way, we'll be calling this a Heisenberg representation later. So we can look at, of course, the unitary families that the position and momentum operators generate. So looking at V, multiplication by the function gamma on G, and U sub X, translation of a continuous function by the element X, these two unitary representations do satisfy the Weil commutation relation, and of course they're bounded, so we don't have to make any assumptions about a dense subspace on which they would do this. They just do it everywhere because they're bounded. So the question then is this all possible pairs of unitary representations which satisfy the Weil commutation relation? Yes. So that's super interesting that looking at unitary families, necessarily we're thinking of strongly continuous representations. If we consider all pairs that satisfy the Weil commutation relation, we do have a uniqueness statement. However, just looking at pairs of self-adjoint operators, we don't. So in general, the Stone-von Neumann theorem, the classical Stone-von Neumann theorem, which is also called the von Neumann uniqueness theorem, depending on where you're looking, it says that any pair that satisfies the Weyl commutation relation must be unitarily equivalent to a direct sum of copies of the Schrödinger representation V with U. So as a corollary of the Stone-von Neumann theorem, you can say this about pairs of self-adjoint operators that satisfy the Heisenberg commutation relation. If you have a pair that generate unitary groups S and R that satisfy the Weyl commutation relation, then by the Stone-von Neumann uniqueness theorem, S and R have to be unitarily equivalent to the direct sum of copies of V with U, and then you can untwist and say then there is some sort of integration, so to speak, that yields a unitary equivalence between the pair AB with copies of QP. This is really nice, but there's an issue in the sense that knowing only that A and B are a Heisenberg pair, that is to say they share some dense domain on which they satisfy the Heisenberg commutation relation, that does not imply that their unitary families satisfy the Weyl commutation relation. So the Stone-von Neumann theorem is just really powerful. Knowing when this happens is still an interesting question to study. The likes of Dix-Millet and the Flato-Simon integrability criterion have looked at this, but there's more that Leonard and I want to do there as well. All right, so here's what Leonard and I set out to do. Our first goal was simply to say there's a Stone-von Neumann theorem for pairs of unitary representations on a Hilbert space. Can we extend that statement to be about pairs of unitary representations on Hilbert C-star modules? Well, to do this, we're really going to have to define what we mean by satisfying the Weyl commutation relation, because we're acting on a Hilbert C-star module instead of on a Hilbert space. And we need to come up with some canonical representation like we have in the classical case. This is the object that is the unique one. So Leonard and I needed to construct an analogous object, a Hilbert C-star module, analog of L2 of G, and a pair of unitary representations on that Hilbert C-star module. But then we got excited. We obviously have a C-star algebra that the Hilbert C-star module X is over. And we also have a locally compact abelian group G. So instead of simply considering only representations of the group G, could we consider representations of a C-star dynamical system, GA alpha, on Hilbert C-star modules? Okay, so here's what Leonard and I were able to show. Given a C-star dynamical system of the form G, K of H, the compact operators on some Hilbert space, if I have what I'm going to call a Heisenberg representation of this C-star dynamical system, and I'll define that for you in a moment, if I have one of these, it has to be unitarily equivalent to a direct sum of copies of the Schrödinger representation, which I also must define for you. So here's what a Heisenberg representation, not of a group on a Hilbert space, but of a C-star dynamical system on a Hilbert C-star module looks like. So the ingredients we need here are a quadruple. We've got a Hilbert C-star module. We've got a non-degenerate star representation of the C-star algebra A acting as adjoinable operators on X. We've got our pair of representations as unitaries on the Hilbert C-star module X. But this is where we have some new conditions. The first new condition is the pair rho R must be a covariant representation of this C-star dynamical system. And the pair rho S needs to be a covariant representation of this C-star dynamical system, which is trivial, which is to say these representations essentially commute. And we've got the Weyl commutation relation. So really, these two covariant requirements are new conditions that Leonard and I needed to have in order to get a uniqueness statement. And I guess it's also important to note that this wouldn't be super interesting if what we had constructed here did not simplify to a classical Heisenberg representation when you replaced the C-star algebra with the complex numbers. Okay. And as a note, I'm sure most people who are watching this are aware, but just in case, not all Hilbert C-star modules have orthogonally complemented submodules, which makes them particularly difficult to deal with relative to Hilbert spaces. So now I need to tell you what mine and Leonard's canonical representation is that everything is going to be unique to up to a direct sum of copies. We start with the algebra of compactly supported continuous functions taking values in the C-star algebra A. And of course that is a right Hilbert A module, but it's a right Hilbert A module with the trivial right action, but we are going to ask that it have a twisted right action via the action by the group G on A. The inner product on this algebra will be a twisted inner product. And then completing this, we get L2 of G A alpha. So that is our Hilbert C-star module X. Next, we need a representation of our C-star algebra A acting as adjointable operators on this Hilbert C-star module. We're going to just take the very natural multiplication by A. A can be considered as a constant function on G, so that's what it's doing, is left multiplication. Okay, so we've got X, we've got a non-degenerate representation of A. We also need our representation of our group. That was called R in our Heisenberg representation. And here, it looks an awful lot like left translation, but we're going to twist at the end. So we have a twisted translation representation. And then the last ingredient is the representation S of the dual group. And this is going to be identical to capital V when we have a trivial action. Okay, so this quadruple with this Hilbert A module, this representation of A, this representation of G, and this representation of G hat form our canonical object that we call the GA alpha Schrodinger representation. Great. Of course, this wouldn't be super interesting unless our object reduced to the classical Schrodinger representation, which it does. Okay, so before we get started trying to show that all of our Heisenberg representations must be unitarily equivalent to our Schrodinger representation, we obviously need to check that our Schrodinger representation is a class of Heisenberg representations, and it is. So I'm going to kind of go back and forth between the proof of the classical Stone-von Neumann theorem because Leonard and I followed that and along the way had to make generalizations, but the roadmap was already there. So the classical Stone-von Neumann theorem starts with essentially the way they're going to build this unitary equivalence is by looking at this cross product C-star algebra and noting that it is isomorphic to the compact operators in L2 of G. So our generalization of this was we needed to show that this C-star algebra and a cross product via the left translation with the diagonal action of alpha is isomorphic to the compact operators on this Hilbert A module. Also, we need to know what this isomorphism is actually given by. So the classical one is the integrated form of C with U, where C is just multiplication and U is translation. So all we're going to do is replace little c with big C and do the exact same representation, but as adjointable operators on that Hilbert A module. So it turns out that big C with little u is a covariant representation of our C-star dynamical system, and it implements this isomorphism for us. Okay. So to show that this is actually an isomorphism, it's not too hard, but we have to note that this C-star algebra here, let's call this C, our Hilbert A module L2 of GA alpha is in fact a CA impermittivity bimodule via Green's impermittivity theorem. And we know that, generally speaking, if X is any BA impermittivity bimodule, then you actually get that the left-acting C-star algebra is isomorphic to the compact operators over X with right action by A. And by the way, this is in Williams in case you want to check this out. So we verified that this canonical isomorphism here is actually implemented by the integrated form of the covariant pair C with U. Great. So we have this isomorphism with the C-star algebra from the compacts. If I take this as the inverse of that map. Okay, so we're actually going to build a representation now onto the adjointable operators on X, and this construction is also going to follow the classical Stone-von Neumann theorem's construction. So if you have a classical Heisenberg pair of unitary representations on Hilbert space, you can use the inverse Fourier transform, and you can build this representation pi s of the C-star algebra C0 of G. It turns out that, assuming that you already have a Heisenberg pair, so they satisfy the Weyl commutation relation, you automatically get that this constructed representation forms a covariant pair with R. And that gives you this covariant representation of this dynamical system. So Leonard and I did the same thing. Given a Heisenberg quadruple, we constructed a covariant representation where we had to generalize this little pi s with something a little bit more robust to handle covariance with rho. And we have a covariant representation of this C-star dynamical system. And it's known that in the classical case, the integrated form of that covariant pair is a nice representation on a B of H. And so our integrated form is a nice representation of this C-star algebra on as adjointable operators on X. So now, like in my picture a few slides ago, we have a representation of the compact operators acting as adjointable operators on X. And classically, that representation, this composition, is what you need to get your unitary equivalence up to a direct sum of copies. So, classically, this representation this might have been proved prior to Arbison, but given that this is a non-degenerate star representation of the compact operators on a Hilbert space, you necessarily have that it must be equivalent to a direct sum of copies of the identity representation. So, what Leonard and I needed was essentially to have some information about what this composition had to do, given that you have compact operators, just not compact operators on a Hilbert space, but on a Hilbert A module. So along the way, Leonard and I proved something that we think hasn't been proven before. If I have a Hilbert K of H module, and I take any non-degenerate star representation of the compact operators on the Hilbert K of H module as adjointable operators on X, then you must be unitarily equivalent to a direct sum of the copies of the identity representation. So this is a full generalization of the result here. Great. So using this theorem, we are able to get that the composition of these representations must be unitarily equivalent to a direct sum of copies of the identity representation. And also just to note, this is why we did need to restrict to compact operators here for our C-star algebra. And so the final observations to make here to prove our theorem are simply that given that we have this and it's unitarily equivalent to a direct sum of copies of the identity representation, we get that psi must be equal to our representation, our integrated form of M with V. So we get that these two integrated forms must be equal. And therefore, these integrated forms are unitarily equivalent up to a direct sum of copies. And untwisting, you're able to show that rho is unitarily equivalent by the same unitary to a direct sum of copies of M, same for S, and same for R. Thank you.